Hello friends, welcome to my channel. Let's have a look at problem 1804, Implement Trie II. Trie is also known as Prefix Tree. So this video actually is a follow-up video for problem 208. So that problem is the implementation of basic prefix tree. And in this problem, we added some requirements such as this function count words equal to. So this asks to return the number of instances of the string word in the trie. And another function added is count word start with. So this asks to return the number of strings in the trie that have string prefix as a prefix. So another function is erase. So erases the string word from the trie. So this is the main problem and the main task. So here are some examples. You can read through the explanation to digest. So the constraints for this problem are the following. First, the length of the word and the prefix are bounded above by 2000 and bounded below by 1. And secondly, the word and the prefix consist of only lowercase English letters. So this is the number of calls for the function insert, and count word equal to, and count words start with, and erase. So it's guaranteed that for any function call to erase, the string word will exist in the trie. So this one is sort of important. Also, this one is also is important, right? Because we know the possible case if we're using dictionaries. So with that done, let's look at the implementations and some remarks. So for this problem, our implementations will be parallel to those in problem 208. So again, we're going to give two flavors or two implementations. So the first one, I'm going to use a dictionary object as a trie node. So the case in each node will be the lowercase English letters as specified by the constraints. And we're going to use two special keys or two special strings to record and retrieve the countings corresponding to the two functions count words equal to and count words start with. So here I'm going to use this string prefix and this string count. You can choose any as long as you can make it consistent. So this is not essential, but just the two names. So this is the first implementation. And in the second implementation, we're going to use explicitly a trie node object. So you can just regard it as a node. So this will add a little bit abstraction and based on the first implementation. So here I'm going to use two attributes. This actually corresponds to the two keys in the first implementation. So I'm going to use count start with. So this corresponds to the prefix key above here. And also I'm going to use a count. This count the whole words. So this corresponds to the count above. So with that said, so we know our overall plan. So here the overall plan to reiterate are the following. First, I'm going to give an implementation based on using a dictionary object as node. And then in the second implementation, we add a little bit abstraction to make it more formal. So with that said, let's first do one implementation. So in this implementation, what I'm going to do is to use a dictionary object as a trie node. So for this, let's write the initializer like this. So trie. So here's a dictionary. So here I'm going to use lowercase English letters. Let's see. And this is the prefix and the count as the possible case. So this is the just for some pre announcement or conventions. So after that, we can first implement the insert method. So this is actually very routine now. First, let's get the current node or current dictionary. So here I'm writing current dictionary. So this is just to remind ourselves. So here it's a trie node. It's actually also a dictionary object. So I'm going to call this one, right? And then we're going to iterate over the characters of the word. So for character in word, so basically we want to check if the character as a key is in the dictionary, current dictionary. If not, we're going to add that key to the dictionary and then assign it a value that is a trie object or dictionary. So this will be the so in order to save some lines, I'm going to use the setDefault method for the dictionary. So what I'm going to do here is so I'm going to use assign and update in the same line. So basically what I'm going to do is do this current dictionary. So I'm going to use setDefault. So basically I'm going to check if character C is a key in the current dictionary. If not, so whatever I'm going to do is to assign it like this, prefix. So here the counting will be 0, right? So initially. So because this setDefault will return something. So either return the current the value corresponding to the key if the character is a key in the current dictionary. Otherwise, so if we do not specify this default value, it will return null. So in this case, it is going to return this one, right? So here we can also, because it has returned, so we can update the current state like this. Notice that this line is playing two roles. First, do the set, and then do the update of the dictionary state. So with that said, so what we are going to do is that we update current dict. I'm going to increment the prefix by 1, because once we add a character to the dictionary, then the corresponding prefix, we know it's incremented by 1, so we modify the value corresponding to the prefix. And then what we're going to do after the for loop, we insert the word to the trial abstract data structure. So in this case, I'm going to add the final state of dictionary, and then we use the key count, so to count the whole word. So this should be equal to current dictionary get key, right? So get count. So then if this count does not exist yet, it means that we first insert this word, so the counting would be 0. And then basically we add by 1. So because this return is null, so that's it for this function. So after that, so I guess we can do count words equal to and count words start with. So this two function is actually quite similar to the check words existence and check prefix existence, right? So it's just an augmented or stronger version, right? So here first is the same thing. We are going to get the current dictionary or current node. So that is self try, and then we are going to iterate over the word. So for character in word, so if character not in current dictionary, it means this C is not a prefix even. Then the word it means that the word does not exist in the trial data structure. So in this case, we are going to return 0, right? After the if check, if nothing has returned, we need to update the dictionary state to the next level. So that is dict equals to current dict C, because C is a key after this if check. So after the for loop, basically we are at the end of the check. Then what we are going to return is the dictionary state. So what we want to return is the count, right? Because this is the count of whole words. And then if the count is not a key to the current state of the dictionary, then we're going to return default 0. So this is the count words equal to. So you need to compare this to compare with the function check word existence in the trial, right? So this is similar, but here we need to return not only the existence but also the counting, right? So it's a stronger version. So this is the count words equal to method. So now let's look at the count words start with. So here actually they are sort of the same, but what we are going to return is count dictionary get the prefix, right? That's what we are going to do. So, but for this purpose, we can copy this piece of code, and then we do some modifications. So, because here we are checking prefix, so we are going to change this to be prefix, and then up to here, what we are going to check is prefix, right? So this is the count words start with method. So next, let's look at the erase method. So basically for this, we need to modify the two attributes, that is prefix and count, right? So this is sort of the reverse operation of the two functions count words equal to and count words start with. So here, what I'm going to do is, again, first let's get the current dictionary state. So hit self try. And then we are going to iterate over the current word. So notice that we are deleting a whole word here, as explained here, or assumed here. It's guaranteed that for any function call to erase, the string word will exist in the try, right? Then what we are going to do is for C in word. So what we need to do is that we can get the current dictionary, right? That is current dict C. So we can call this because we know that C must be a key of the current dictionary. Then what we are going to do is first we are going to decrement the prefix counting by 1. So this is one thing. Another thing is that after we end at this exit this for loop, so we need to also modify the corresponding count attribute. So that is current dict. So the count. So we are going to decrement it also by 1. So this decrement means that we deleted a whole word, and here it means we deleted a prefix string in the process. So with that said, I guess that's actually implementation of the trial with the current requirements. So before we move forward, I guess it's better to do a check. Yeah, it passes the example given. Now let's look at the generic case. Yeah, it passes all the cases. So with that done, I guess we finished the first version of implementation. So here, let me give a small summary. Here in this implementation, we used a dictionary object as a try node, and then the keys in each node will be the lowercase English letter or other lowercase English letters. And we have used prefix and count to record and retrieve the occurrence or frequencies of prefixes and words. So this is implementation 1. So next, I would like to add some abstraction to the first implementation. So for this, I'm going to first copy this one, right? And copy this one. Let's see. I'm going to add some separators here, and then I'm going to change this solution class to be v1 just to for later check. And then what we are going to do, this is not this one, but the one here. And then we are going to delete all these things and do the re-implementations. For this, first I'm going to make a quick class called try node. So this is just add some abstraction. As we see from the first implementation, it's not absolutely necessary, but this is more formal, I would say. Try node. So here I'm going to define an initializer or constructor self. So here I'm going to call a children field. This is a dictionary. So then I'm going to call another two. This count initially 0. This count the whole words, and the self. Let's see, count start with. So this is also 0. So here, this dictionary, then we can use nested dictionaries or nested nodes to count keys. And here, this is count whole words. And this is count prefixes. This is the try node. It has 3 fields or 3 attributes: children, count, count with. So you can compare with this is a count field in the above implementation, and here you can count this as prefix fields or attributes. So this small piece of code construct us a try node, an abstract try node. And then what we are going to do in the implementation is that in order to use a dictionary directly, so we can use the wrapper try node. So here, let's do this. Self root, let's see, or node, that is try node. So here I'm instantiated a try node. So this is also the constructor in this class try. And next, we're going to implement the for method. So this is actually up to now very routine. First, let me implement this insert method. First, I'm going to get the root. So notice that this root is a try node, right? And then we're going to iterate over the word for character in word. So basically, we want to check if character is in the keys of the children field. If not, we're going to make a key and associate the value with an empty try and continue the procedure. So here again, I'm going to use update and assign in the same line just to save some lines of coding. So here, first I'm going to do node children. So basically, we want to check if the current character in the is a key for this children field. If not, we're going to make it a key and assign the value as a empty try node. So we do this like this. So we set default, and then we're going to check the character. If not, so we give it a default value, that is an instantiation of the try node. So because the implementation is from the right of the equality assignment symbol, and then we first do this, and then we update this node to be the current state, right? And so this is what we're going to do. And after we update, so we need to know that we need to update count, right? So count start with the increment by 1 because the C is a prefix. Then after this for loop, what we are going to do is to get node count incremented by 1. So this count start with is incrementing the prefix counting, and this count is incrementing the whole words counting. So this is the insert method. So with that done, so we are ready to implement the 2 methods corresponding to count words equal to and count words start with. So as we mentioned, So this these two functions correspond to check word existence and check prefix existence, and their differences are in parallel to the difference of the check word existence and check prefix existence. So with that done, so let's do this with the above pattern. Actually, these things are very routine for now. So let's get the current. Let's get self root. So this is the current node, try node. Then what we're going to do is iterate over the word. Then we're going to check if C not in node children. So in other words, C is not in the key, so meaning that C is not a prefix. So it cannot be a word for sure. So we're going to return 0, right? This is the occurrence. And then if C is in the key of the node children dictionary, so we're going to update this node to be node children C. Notice that this value corresponding to key C is again a try node, right? So that's why we can chain together and continue and put them in a for loop. So afterwards, what we're going to do is to get the node count, right? It's best maybe to write like this. So you can return node count, or you can write it like this. This might be better. Return node get count, and then 0. So this is in parallel to the first implementation, right? So let me comment this line. So this is the count worth equal to. So now we can copy this piece of code and put it in count worth start with. But here we need to modify this to be prefix. And then what we are going to do is to call this part, call this this attribute count. So here I guess I'll make some mistakes. So because this is a attribute, right? So let's call let's call this count start with. Let's see. I'm going to copy this part. Yeah, actually I can copy the whole part. So yeah, this is a function for count words starting with, counting different attributes here. And then for the arrays, the same thing. We just need to modify the count start with and count attributes in each level. So first, let's get the current node. So this is self root. And then we're going to iterate. So for C in word, what we're going to do is to first update the node state. It's going to be node children C, right? Notice that this is again a try node. And then what we're going to do is we're going to count start with. So we're going to decrement this guy by 1. And after the deletion of the whole word, we are going to decrement count by 1. And so because the return for this one is null, so that's it for this function. So up to now, I guess we'd better to first make some test, then make some comments. Yeah, it passes the example given here. And now let's look at the generic case. Yeah, it passes all the cases. Here, actually, this implementation compared with the first version. So we used the specifically or implicitly the try node object, and then we actually write this functions or methods. So this is entirely parallel or similarity with the first version. And but we add some abstraction using the class. So with that said, basically I guess that's about it for this problem or this trial implementation 2. So you are welcome to compare this implementation with the previous problem, that is problem 208, and to compare, to digest, and to devise more elegant solutions. So with that said, I guess that's about it for this problem. If you found the videos here interesting or informative or useful, you are welcome to share and with your friends and distribute. So